Today's seminar. We're very pleased to have as our speaker today Dr. Chris Byrne from Department of Engineering at Western Kentucky University. Chris had an early interest in learning how to make things and in figuring how to make things work, so he carried that through with his undergraduate work, and he attended the University of New Hampshire in Durham and majored in mechanical engineering there. He then attended Johns Hopkins University for his graduate studies, earning both his master's and doctorate degrees in material science and engineering. He then, in that time, he further synthesized his applied and theoretical skills by exploring many aspects of materials science and processing associated with metallurgy, ceramics, plastics, and composites. In his postdoctoral work at Johns Hopkins, his research efforts focused on new methods for making dilithium crystals for transducer applications, as well as further development in carbon-based materials. He was on the faculty at Southern Illinois University at Carbondale and interacted there with partners in the transportation industry associated with the University Center for Advanced Friction Studies. His research in carbon aircraft brakes shed light on challenges that industry faced in making reliable products. He then moved to Western Kentucky University in 2001, and he enjoys teaching undergraduates there and is conducting research in a number of areas in material science, carbon materials, composites, composite processing, non-destructive evaluation, friction, and wear. Today he's going to discuss his research work entitled Another Look at Products from Plant Materials. Thank you, Chris.
Thank you, Nancy. And thank you, everyone. It's a pleasure to be here. It's an honor. I've had a wonderful morning of tours. I thank Monahar for inviting me, and John and PK for showing me around, and everyone else that showed me around. I'm impressed by your facility here. It looks like you're doing a lot of wonderful things and things that interest me. I'm going to talk about a number of different things that excite me and perhaps have some overlap in some of the things that are going on here and interests that you have. And my outline, although I typically don't give outlines in a presentation because most people know what you're going to do, I put an outline together because I'm going to jump around a little bit. I'm going to start talking about historical uses of wood to put things in context, and then how certain industries related to wood help to set up the petrochemical industries that we have today, and then how we look at plants today and their role in today's engineering. In concert with that, looking at charcoal industries today, those that use wood charcoal, and then spend another portion of the talk looking at a little bit of work we did in making bio-oils and improvement in bio-oils, and then finish up with maybe a third of my overheads looking at wood as an advanced material and using it as a template for making certain materials, some samples of which I brought with me. One of my favorite quotes that was written in 1919 seems to me to still be true today, that in spite of rapid introduction of wood substitutes, we're still finding new uses for wood. And I would say that's true for all plant materials. And my perspective is from a materials engineer, how we can use it in engineering materials. But this kind of statement, since humans have been using wood since day one for a variety of reasons, I think this has probably always been a part of a discussion. How can we make something with wood? What can we use differently, or how can we differently use wood? Wood is so wonderful, has so many unique attributes, and several images here help me to talk through some of my perspective on wood and its attributes. It's been used since early times. There's an image of a sarcophagus that we have at our university, and that came to my understanding 6 months ago because there was a question on whether or not that wood was actually used in 3,000 years ago, because the history of it had been lost. So that it was brought to me simply, what kind of wood is it? Is this a fake, because many fakes were generated in the early 1900s, or is it potentially real? Well, one thing I learned over the years is that you can take a sliver of wood and identify what kind of wood it is. So I had them take a sliver off and actually find that indeed under a microscope it has all the microstructure and cellular anatomy of the wood that typically was used back in the Bronze Age for making certain items. So this was Ficus sycamoris wood, just based off of its wood anatomy. And I say that as an introduction. The wood anatomy, there's just a sliver of how the cells go together in the wood, and it is the beginning, at least as you look from the macro scale down towards the micro scale, it's the beginning microstructure that nature has imparted into wood that gives it so many of its wonderful characteristics in terms of mechanical properties and transport properties. And then as you go further down in the size scale, the wood cells themselves, as you probably are aware, are very interesting and relatively complex composites. They contain cellulose, hemicelluloses, and lignin that holds it all together. And these wood cells then are very fibrous with fairly long aspect ratios. And they are put together in certain architectures dependent upon the type of wood that you have. Well, as you go even further down on the size scale, within cell walls, the cellulose molecules are arranged in specific ways. So nature has come up with this architecture from the molecular level all the way up to the cellular level that allows wood to perform so many useful functions. Now, cellulose is got a certain chemical makeup, and that's the majority of the content in wood is made out of cellulose, and many plant materials are high in cellulose. So wood has been around for so long, and you can cut it, you can plane it, you can carve it. We've been using it for building our homes and vehicles since day one. It has been used for heating our homes since early times. It's been turned into charcoal for millennia. For many hundreds and thousands of years, it's been used for producing charcoal. As time evolved and humans got a little bit more adept at ways of utilizing wood, it was the basis of many of our chemical industries, and I'll talk a little bit about that from my perspective. Wood products nowadays are oftentimes referred to as engineered woods, where you may take wood and make particle board or medium density fiber board, or you now have these wonderful long engineered beams and trusses that engineers are putting together, and typically they use the term engineered wood products. Charcoal is still something that's used a tremendous amount, whether you take the historical view of what charcoal is or you take a more modern view such as biochar. But charcoal is still being used in filtration in a role where activation of the charcoal allows it to absorb many things and filter out many undesirable things. It's still being used in cooking in our backyards by virtue of charcoal briquettes and other things that we like to use to cook our foods. In the industrialized countries, these two applications are what I view as the main applications for wood charcoal, either activated charcoal or charcoal made by, say, Kingsford for briquettes. However, charcoal is still being used and produced in what I'm loosely calling developing countries, and I'll talk about that in a minute. But when we put it under the category of engineering with wood, there's also some new activities in conversion of wood to ceramics and carbon composites, and that's what I'll finish my talk up later today. I don't need to walk over there. Okay. I like the internet just as much as the next person. I don't claim to be as adept as my students, but one thing I find is that I can find things that were published 100 years ago at the click of a mouse. So here is a book that's, I forget, 300, 400 pages long. Heat, energy, and fuels. All about combustion of charcoal, coke, and fuel gases, printed in 1908. And I bring this up because now I want to just talk about the history of making charcoal. For hundreds of years, charcoal was produced by a very simple method, and here's just a brief sketch of how it might have been done, where you could either dig a hole in the ground or mound up carefully laid bolts of wood into a pile and cover them with earth or mud or something to inhibit oxidation from getting to it. Light the thing very carefully and monitor it for days at a time and let it smolder to produce a mound of charcoal. This is an approach that was used for centuries and eventually gave way to more modern, I'll use the word loosely, modern approaches in which engineers found ways to do it in retorts. So this old style production of charcoal essentially went away with the 1800s. And it was replaced in the 1800s, again, pages from that same 104-year-old book. It was replaced with the newer version, which was the ability to pyrolyze wood in retorts. So steel came along, allowed us to, or allowed humans to make charcoal in steel retorts, which meant they didn't have to pile dirt over the mound to inhibit oxygen, allowed for more controlled thermal decomposition. And the sketches on the left are meant to indicate that. And it could all be housed in a facility where it would be a little bit more convenient to produce wood charcoal. Wood charcoal in those days was very important because it was a necessary ingredient for making steel. Well, with the development of the steel retort, we were able to then capture the pyrolysis gases that come out, and we could then generate other products from that process, something which I know many of you are doing in here now, and something which began what I call the modern day chemical industry or petrochemical industry. Wood charcoal being the precursor to how we learn to make petrochemicals. And there's a chart here with composition of liquid fuels from a number of different sources, such as tar oils and schist oil, coal tar, and somewhere in there there's even from wood products, or maybe it's on a different page. That old industry where charcoal was made by putting wood into mounds and covering it and taking days at a time to monitor the mound so it didn't go out of control, it is still being used in some places in this world, very great extents. In Brazil, and this is something just pulled off the internet. There are many hits that you can get when you look up charcoal in Brazil. But charcoal now is one of the main sources of energy used in the production of pig iron for steel in Brazil. A technology which in our country and in European countries was developed centuries ago, and the process for making charcoal was used centuries ago. Still, charcoal is being used in Brazil, and they're taking down quite a bit of forest, and sometimes illegally, and producing charcoal in old-style charcoal mound method. Many issues related to this that one can imagine, and here is another snippet of information of how they're working, making charcoal in Brazil, or had been. Right down here, all these little kilns, these are actually ceramic type kilns, but they're basically mounds that wood is put into, and nothing is done to capture the vapors that come off. So as many of you know, when you pyrolyze organic material such as wood, you may have 20 or 25% mass left in charcoal, but 80% of the mass is going up the smokestack. So this is one of the challenges they have been facing over the last 2 centuries, that even according to the study coming from Brazil, charcoal production has not evolved. It remains basic and primitive. And of course that has impact on charcoal workers, let alone the environment. So I don't know if you can read it, but one of the challenges in Brazil, as you all know, they're taking down vast amounts of the tropical forests, part of it going into charcoal, part of it just going up into the atmosphere. But so deforestation is a part of it, but you could also imagine the pollution that comes from it, and perhaps the waste, more importantly to me, the waste that they have. I just love that one. I had to share it. It's just okay. So that's my brief history of charcoal and plant products and how it has been used over the years. And now if we take a look towards some of the activities that are going on today, and I just realized that you don't have the same background I have on my overhead. I have a nice cellular structure of wood in the background on my slide that you can't see, so it's a little bit bright for you. I apologize for that. Again, going back to the internet, when you do a Google search on biofuels, 2.9 million hits. Now, granted, you know as well as I do, there's not a whole lot of interest in 1.9 million or 2.9 million of those, but there are a lot of them that are very interesting. And this one just seemed appropriate for today. So from the earliest days of the internal combustion engine, these visionaries dreamed engines would run on fuel made from plants. This is so some of the things we're visiting today were not new to us in this decade or this century. These were thoughts that have been going on for quite some time. So you have Henry Ford looking into the idea of getting fuel from plants, and people like diesel. And those interests kind of faded away. Recognize that was a time in the early 1900s when the petrochemical industry was still somewhat in its infancy, 20 or 30 years old. But petrochemicals have taken, and fossil fuels have certainly taken over as our main source of fuels and energy. So today we go from thinking about fuels from plants, and we now use the modern term of biofuels. So we have biofuels, and then we have pyrolysis oils. And if you do your Google on pyrolysis oils, and hey, I do this every once in a while. I did this a week ago for this slide, and I was amazed because the last time I did it was maybe 4 years ago, 4 years ago, and the amount of information that's out there now is staggering. 2.4 million hits when I do pyrolysis oils. Well, the one that I wanted to pull up because I enjoy pictures, we've got a faculty member today, or there's a faculty member in Massachusetts that's got this little pilot plant for, it looks like it's on a trailer, for going around making pyrolysis oils from plant products. Wonderful idea. I don't know the individual. I'm not here to express any support or voice any opinion on what that person is doing, but this is just a snippet of information for the type of activity that's going on around the world. Making oils and fuels by the thermal degradation of plant materials. And I would add, in my opinion, the most important aspect of all this is efficient use of those materials. Not allowing 80% of the mass to go up into the atmosphere, but capturing that mass when you're making a biochar or a char material and using that vapor for a useful purpose. Okay. a while ago I mentioned the idea that I placed modern day charcoal use into two main buckets. One bucket being activated carbons used for filtration, the other bucket being for cooking in our country, let's say, or in European countries. Here's a paragraph, a long one, which you don't need to read, that comes from a company in Hawaii called Big Island Carbon. And I came across this a few months ago when realizing that a well-known carbon scientist left Oak Ridge National Labs to join this effort in Hawaii. Probably not a hard decision on his part, but this is a gentleman that has spent most of his career looking at carbon materials, whether it be for carbon fibers or for carbons for nuclear moderators or for activated carbons, and is well known in activated carbons, Fred Baker. The thing that this has that's relevant for us today is here is what I see as one of the leading efforts in more efficient use of the biomass material in the production of the traditional activated carbon. He's leading an effort by this company to get more use out of the feedstock, in this case macadamia nut shells, for producing activated carbons. They are taking the gaseous byproducts and not just burning them to keep their kilns hot, but they are actually pulling it out as a pyrolysis oil, which they then use to run a steam generator, burn it and run a steam generator, and use that for generating electricity. All this biofuel to generate electricity, all this to, in my opinion, more effectively use that plant material. I have visited plants that make charcoal. Kingsford, which is owned by Clorox, and other smaller companies that make hardwood charcoal for our barbecue grills. And these are efforts where I would estimate only 50% of the mass is really being used. 20% going to charcoal and 30% going to burn for useful heat. The rest might be burned, but is going to non-useful heat and waste heat. So in the industries that make activated carbon, they have a long way to go to get more energy out of their systems, and this is one that is actually doing a good job of it, in my opinion, or on the right track. And that's why they've hired someone who is very well known in the carbon industry, so they can continue to make good activated carbons and do it in a more sustainable fashion. But there's a lot of room for us to improve. So, if we can develop better technologies for use of the pyrolysis byproducts, then I see that there are industries that are going to benefit. Those that are making activated carbons, and this company is doing it. Those that are making charcoal, such as Kingsford or Cowboy Charcoal or whoever it is that might be making charcoal that you might use in your barbecue. Or other industries are maybe the emerging industries that are looking at these green fuels and chemicals. So the idea is, how can we better more efficiently use these plant byproducts? So transitioning now into another part of the talk, I want to introduce a little bit of work that was done by a graduate student of ours in chemistry, and part of her thesis work is what I'd like to just touch upon. The overall objective was to look at chemical modifications to the wood or the biomass precursor before carbonization to see if we could enhance or alter the value of the pyrolysis vapors. So you could look at the bio oils that would come from it. And a little bit of rehashing what we already know. You know, the use of thermal degradation of plants, you can consider it carbon neutral or maybe even carbon negative if you do it right. It uses a renewable feedstock when you use plants. There's growing concern over the carbon emissions, and we do have, as everyone knows, depleting fossil resources. So these are concerns, And maybe thermal degradation of plants is one way to help address this. I'm going to skip past this. Well, I'm not going to take much time on this, but in her research, she looked at an effort in making a bio-oil. And there's a little flow diagram which suggests all the different routes one might take that are related to bio-oils. And oftentimes what you see people doing is flash pyrolysis or heating of the plant material real fast. And the intent is to have higher throughput, because we want to be able to have technologies which we can scale up and make efficient by having high throughput. So flash pyrolysis helps us with that. It also might alter the eventual yield of the byproducts. And then there are several different ways that this production of bio-oil can go. You can get charcoal, you can get gases, you can get liquids. The liquids can be used in a number of different ways. And you've got applications for charcoal. And you talk about activated carbons for filtration or biochars for adding to the ground. There are many applications for charcoal, certainly for the heat during the firing process, electricity generation, and so forth. So these are things we know about, but things we're looking in more earnest because we see ways that we can do better. So, in this master's work, looking at volatile products from untreated wood. First step of her process was just take some wood, something like yellow poplar or yellow pine or tulip poplar, and those are typical North American woods, and look at the volatile products that come off of them when you turn that wood into char. And thus we use the term untreated wood because the first step is look at wood that's untreated, and then let's treat it and see what kind of products we get. So her main focus was to first look at how heating rates might influence the byproducts. Whether you heat slow or fast, is that going to influence the types of compounds that come out? And overall what we found is that wood pyrolysis using very fast or very slow, the overall products were virtually the same. However, when we look at apparent different temperatures at which they are decomposing, and we look at the comparison between very fast or very slow pyrolysis, we see the compounds that come out at different temperatures being different. Excuse me. It's supposed to be pointing there. So the volatile products appeared to be different at the different temperature ranges. Okay, well, going on and looking at how we might improve those products that come out from the distilling the vapors. One area of research that maybe some of you are familiar with is how can we increase the energy content of the biofuels, and some area that was found that seems to be of a fruitful path to take is to look at furan compounds that you might be able to get into the biofuels. So these furanics are these compounds that tend to have a higher energy density compared to ethanol. So the thought is, let's get more of these compounds and some of their derivatives into the bio-oil, and we'll have a higher energy content fuel. Well, some people have been looking at how you can use catalytic processes to change those pyrolysis byproducts, and the approach that we took was, was to see about treating the wood beforehand and see if we can alter the products. So a big jump, yes. Absolutely.
Particular temperature that tries with something, or
particular compounds. I don't have that information here to be able to tell you, and I don't remember it well enough to say. However, it is certainly reasonable to presume that you would get different compounds, from certain temperature ranges because of all of the different compounds that are in something like wood, they tend to decompose at different temperatures, with the hemicellulose going at the lower temperatures on average, the cellulose decomposing at a little bit higher temperatures, and the lignins going at the higher temperatures still. So you would presume different compounds in the different temperature ranges. But I don't know them well enough to be able to articulate just which ones they were. Okay, so you can use, I guess, standard distillation methods that might be used in petrochemical industries, such as catalysts, or what this student set out to do was look at a pretreatment of wood with sulfuric acid, where sulfuric acid will essentially begin the degradation of the polymers at room temperature. And so there's a lot of information on this, and I apologize for putting such a table up there, but the bottom line that we got from the series of tests that were conducted is that you can increase mass yield of the charcoal by so again, it's how typically the mass yield of I'm misspeaking, I'm sorry. Mass yield of charcoal is typically on the order of 20 or 25%. Therefore, the mass decrease should be on the order of 80 to 75%. So in this left-hand column, the right-hand column, what we found is that the greatest carbon yield, or the least mass decrease from carbonization, occurred with a sulfuric acid pretreatment of 10%, which means essentially that less goes up the smokestack. So we have a maximum charcoal yield when we do a sulfuric acid pretreatment. And then what was looked at by mass spectroscopy was looked at some of the different compounds that come out when you look at a particular wood species, and you look at when it is untreated versus treated. In this case, heated up relatively quickly. There are many compounds. I don't know. Does anyone know how many compounds you might expect to come out of the decomposition of plant matter? Is it over 100, or over 1,000, or over 1,000,000? I don't know. But it's many more than I could begin to get my hands around. The thing that I'm going to point to is, by and large, the two on the right, if I can use the right button, the furanitics, and then the furfurols. By and large, what we will see as we go through the next 2 or 3 graphs is that treatment had an influence on the byproducts, treated being in blue and untreated being in red. These compounds went away when we treated. This compound came up when we treated. Okay? Yes? These are the areas from the mass spec. They're not actual units. Yep. It was the simple way of comparing. Okay? And if we look at slow, instead of fast heating, slow heating, we saw a little bit of difference, but by and large, treated versus untreated, you've got this compound going away with sulfuric acid treatment, and then these compounds coming out in a greater amount with treated. Again, the furan compounds. So it happens whether you go fast or whether you go slow. Okay, and then just treated wood, fast versus slow, just the sulfuric acid treatment. And we see a little bit of difference in the amount of compounds that come out, whether they're heated slow or heated fast. So the long and short of it, and I don't pretend to know this as well as the master's student that did it, the long and short of it is, oh, I've got one more slide. I'm going to go past it. That the sulfuric acid pretreatment of the wood decreased the abundance of the phenol compounds and increased the abundance of the furan derivatives. So that's what we wanted to take away from that. If the furan derivatives are an advantage in the biofuel, then this might be one way to go about doing it pretreatment. The other aspect which that comes from this is some TGA work, is that if you look at the mass versus temperature of treated versus untreated yellow pine, then what you find is the untreated wood decomposes roughly after moisture is driven off, mostly between 275 and 400 or 450 degrees centigrade. The greatest drop-off being somewhere around 350 degrees. Whereas the treated wood begins its decomposition at significantly lower temperatures when measured in this way. So we have different temperatures required when treating it to get this kind of decomposition, and we got greater mass or greater amounts of charcoal when we did the pretreatment. Just as a picture to emphasize the influence on the solid product from carbonization, you go from a wood block to a charcoal block, this one having been pretreated and heated to 600 degrees centigrade. One that wasn't pretreated and heated to 600 degrees centigrade. Clearly there is dimensional changes that occur, and with pretreatment we alter the dimensional changes and the mass yield. This becomes a segue slide into the next portion of my talk, because what got me into all this is solid carbon materials. My interest in wood goes back a long ways, but once I started to look at carbon materials for carbon fibers and fiber reinforced polymers, I then got into more detail on carbons and looked at carbons from plant materials and how to use those. So my interest is in charcoal and how can we use it differently. So the semi-summary from, I call it a semi-summary because it's just from that master's student's work. Improve charcoal yield, improve charcoal yield using pretreatment. Decrease phenols and increase furan derivatives using the treatment. And temperatures change when we use that heat treatment. Temperatures of decomposition change when we use that heat treatment. Okay, next category. Going back to the charcoal side and away from the pyrolysis byproducts that go up the smokestack, this is something that I began back in the 1990s, and it's a materials processing approach. Make solid materials. Using plants as a template. And it truly is for plants, but I'm going to continue to talk mostly about wood. As you know, you heat wood with to a high enough temperature without oxygen around, you're left with charcoal. And that charcoal, or the carbonization of wood, creates a carbon skeleton. The skeleton is that cellular structure that was there in the original wood. That skeleton creates a framework for making into a variety of advanced materials or engineered materials, if you will. Since the beginning of the development of this technology, people across the world have been looking at making ceramics from wood, which I'll talk about very briefly. What I'll really focus on is how we've been working down at Western Kentucky University on making a carbon-polymer composite out of wood charcoal as a means of replacing ebony in musical instruments. So the technology that we first developed in 1990s we originally called it cellulose-derived composites, and it's one that builds upon these natural materials Can produce a bunch of different materials, engineering materials that industry uses, whether it be ceramics, carbon-based, or composites. It has materials with unique properties, and it can, in some cases, enable simplification of production, especially if you look at ceramics. Still in early stages of development, even when you look at the probably over 1,000 papers written on production of ceramics from wood, is still in its infancy. No one yet has produced any, has been making money off of new materials from wood, not yet, but no companies are developing it right now and making money off of it. It is a patented technology, but that's less important. So there's my flow diagram for cellulose-derived composites. You start with some kind of wood product or plant material. It can be a monolithic stick of oak or poplar or pine, whatever you want, or it can even be something like medium density fiberboard or paper or cotton fabrics. You pyrolyze it. For the first part of my talk, we tap off of that pyrolysis process and capture the vapors. And again, that's a technology that really had its origin in the middle to late 1800s with the evolution of the steel retort for creating charcoal. You get a charcoal out of it, though, and you can pre-shape that charcoal. The charcoal, if you do the pyrolysis right, has structural integrity. You can mill it, drill it, shape it, turn it on conventional machines. Then you can convert that pre-shaped charcoal into a whole host of materials, whether it be a carbon-carbon composite, a porous carbon that you might activate and use as a monolithic filter, carbon-polymer composite, which is going to be the main thing I'll talk about as a finished product, or ceramics. So there are three main steps. You get your renewable wood, you carbonize it, then you convert it. And the carbon-polymer version that comes from this process, we're going to refer to as ForestPlate. Another visual on the upper left, where you take balsa wood, a stick of wood, you make it into charcoal, and you have volume and dimensional reduction. The graph here shows how you can select a variety of different woods from something very light like balsa wood with a low density up to something very dense like lignum vitae, which is high density, and several different wood species in between, all with different densities. And when you carbonize it, you get different carbon yields from each of them, and you get different volume reductions for each of those wood species. When you look at the char density, the char density follows nicely along with the wood density. On the y-axis is a normalized scale for whether you're looking at char density, carbon yield, or volume reduction, just so I could throw it onto one busy graph. Normalized to the heaviest wood sample. So what this tells me is that, first of all, if you do the pyrolysis step right, you can make charcoal without forming cracks. It has structural integrity. The dimensional changes are predictable. The density of the carbon structure is going to be something you can select based on the precursor wood. And we've gone through and done all these different wood species and other plant species as well. Okay. Are we going to run out of memory in this recording, or do I have to stop exactly at 1? I only have 75 more slides, people. You're awake because you haven't had lunch yet, right? Okay. So taking the carbon skeleton, you call it carbonized wood, you can call it biochar, it's charcoal. Infiltrate the pores of the charcoal and you make a carbon-carbon composite. Carbon-carbon composites used in high-temperature applications such as rocket nozzles, brakes in aircraft, and so forth. So carbon-carbon is a refractory material. Conversion to ceramic. This was a piece of redwood. It now, where all what used to be cellulose and lignin of the cell walls was converted into charcoal, was converted into carbon, and then that converted into silicon carbide. And that picture is there because it's so beautiful. It shows all these silicon carbide crystals. And it retains that cellular microstructure that the wood originally had. Bamboo converted to silicon carbide. Paper converted to silicon carbide. So that's the conversion of, in the cellulose-derived technology approach, that's the conversion to ceramic. And there are several ways to do it into ceramic, like a silicon carbide or so forth. You can do it by metal infiltration, liquid metal infiltration and conversion. You can do it by particulate metal preform, so you can make a compressed board with metal already in it, in pressed board out of wood shavings, wood dust, wood flour, and you can form something like a medium density particle board with metal already in it, heat and convert that. You can use metal vapor infiltration at elevated temperature to convert the carbon into a ceramic. Use sol gel infiltration in the wood before carbonization or after carbonization, and the sol gel brings in with it the metallic elements that can combine with carbon or can exist after heat treatment to form a ceramic. And then the carbon-carbon, by any standard route almost, liquid infiltration and densification of the matrix, or by chemical infiltration and densification. All these routes have been taken for making ceramics from wood. But what I'll finish off with in the last half a dozen or so slides, what about taking the charcoal that has structural integrity all its own and infiltrating it with a resin? I'll pass 4 samples around just at random so that I can get people looking at things. Some are prepared a little bit more carefully than others, and some of them may even be shown in an overhead, I don't know. There are many ways of making carbon polymer composites, and the traditional ones are fiber, carbon fibers with a variety of precursors used to make them, whether it be pan or pitch fibers, and then those fibers are used as are then glued together with a matrix, and the fibers are there to carry all the structural loads. The matrix just glues them together. However, in this case, it's a carbon polymer composite by virtue of the fact that it has 2 phases. It has a carbon phase and a plastic phase. The carbon phase is not there because it has as great structural integrity as a nicely engineered carbon fiber. It's there as a consequence of the degradation of the wood, and it has that anatomical structure that nature provided it. So it has all the grain structure of the precursor wood. It has, and you can convert it into this carbon polymer by vacuum bag techniques or by resin transfer molding or by a variety of other projects that are scalable to large size. And you essentially just infuse the wood pores with resin. That resin then solidifies or cross-links to leave you with a 2-phase material. In the case of the samples going around, they're in epoxy and carbon composite. And you see all the grain features, Rayflex in that sample. You do it to a variety of different sizes, and you can machine it and shape it. We've been developing it quite a bit. These are actually old pictures from 10 years ago, but we've been developing quite a bit at Western to look at ways that we can produce this in an efficient way, in a reliable way, and to characterize the properties of that material that's floating around the room. It has all those anatomical features, the microstructure that's in wood. This is the lumen inside a cell with pit apertures between cells that in the wood allows fluids to transport between them. All those features retained. You see good wetting of the epoxy to the carbon or the polymer to the carbon, and these are just two different views based off of whether you're looking along the longitudinal direction or along the tangential direction of the wood. So full densification is possible using the right approach. You get a material that you can shape using conventional tools. You can polish it to give it a high luster. It has all the grain features, and it is dark like ebony wood. It has strength. This is a compressive strength. Surprisingly enough, the wood charcoal in compression with the grain was stronger than the precursor wood. When you infiltrate it with the resin, you get twice or more of the strength in compression against the grain. And then you see, because I like to break things, that's the way, I like to burn things, that's my last name, Byrne. But I also like to break them, so I have to break them, and there's some pictures of how they all fail. Wood, charcoal, and the composite. One of the main steps in doing this right, for whether you're making the ForestPlate or you're making ceramics using this process, is the carbonized wood has to be made in such a manner that you don't get cracks and that you can efficiently use the whole volume of the charcoal, which means essentially don't let it warp, split, crack, and so forth. So we've been able to accomplish that and get, here's boards that were, 6 inches by 6 inches in dimension. That size, because that's the limit of what our furnace would allow us to make. You can take charcoal and you can mill it on a lathe. That's just charcoal being cut on a lathe. We've got a little chess set made out of it. You can turn the ForestPlate on a lathe, and that piece is actually floating around the room. I just realized that. So is this piece. That's a roughly a 5-inch by 5-inch board that's been converted. But what we're doing is we've tested properties like wear resistance, flexure strength, impact resistance, and we've made comparisons to materials like countertop materials. It compares very favorably to Corian countertop, for those of you familiar with that product for kitchen counters. It compares very well with that, both better in cost and just as good in wear resistance. Students were nice enough to make a nice little table for my office. We are right now looking in earnest at the musical instrument industry. This is a pickguard that was made out of ForestPlate. And the musical industry is one area because really the place to go with this is a place where the visual characteristics are held in high regard. And people are very accustomed to ebony and other exotic woods and musical instruments that are being depleted even faster than our fossil fuels. Whoops, wrong one. Knife handles, gun handles, since we're in the part of the country that likes weapons and so forth. Gun handles, knife handles, stick shift knobs. Or what's really going to hopefully pay off is components in the musical industry. There's the guitar with a ForestPlate bridge, ForestPlate fretboard and head. Here's a ukulele being made, and this is just the raw ForestPlate as the pickguard. Less expensive than ebony. It will be here longer because ebony is just about gone. Has anyone heard about Gibson guitar getting raided last summer by the federal authorities? Did you hear about that? They were being charged with having illegally brought in ebony. The bottom line is there isn't much ebony left. And when I visited Martin Guitar, they showed me a couple of rooms that weren't any bigger in volume than this room. And they said, this is all the ebony we expect to ever get. We don't plan to get any more. So it's going away. Well, as it turns out, either by luck or by good engineering, you decide this ForestPlate material has acoustic characteristics very similar to ebony, similar types of acoustic velocity, similar types of attenuation, and similar types of anisotropy. Plus, it takes a shine. You can polish it. This is just polished. And so it has an appearance that's still wood appearing. It has wear resistance that is as good as, is better than most woods and as good as some of our countertop materials. And it is ready to be put into musical instruments, whether it be string-based or woodwind instruments. So that's where I see the first money-making opportunity for cellulose-derived composites to come from, is in the musical instruments industry. And that's kind of a restatement of it. ForestPlate, or carbon-polymer composites. No other material out there. The important part is we're going to sustainably use natural resources in this country. We're not going to use exotic hardwoods. We'll use something like yellow pine, which probably is everyone's deck outside the back of their house. It's all yellow pine. It's very common. We have decorative markets that are easy to get into simply by virtue of the appearance of that and the feel of that. Cost point might be an issue for some markets, but certainly not for areas that are accustomed to high price tags like musical instruments. We're ready to scale up. We haven't yet. We're still producing it in the lab, but we're ready to scale up, and we're having discussion with partners to be able to do so. So what I have hopefully done is given you enough for now. I've talked a little bit about my glimpse of where plant materials have historically been used. When you think about forming charcoal and how industries have come off of forming charcoal, what we're doing with those industries these days, and what we can do even better these days. And then something that I think is a little bit unique is what can we do differently with that charcoal or carbonized wood? We can form these other materials out of it and make some interesting things. So I'd like to thank you all for sitting and listening to some of my thoughts and looking at some of my snippets of research information. I'm honored to have been invited here. I thank Monahar for inviting me and everyone else who has been giving me a wonderful tour this morning. I don't want to be remiss in thanking some of the people that have contributed to this. There's always a few people that you interact with over the years that stand out in your mind for years and years and years, and there's a partial list of them here that have been direct contributors to this research that I presented. And I think we're still in an exciting time for this research. That quote I had in the second overhead, there's still interesting and new things we can do with wood and plant materials. So I'm excited about what I do, and I'm really excited about seeing all the things that are going on here. I think there might be some synergy. I think it's good work that's going on here. I think your focus is what I believe is important, which is how can we use these resources the planet has in a more sustainable way. So thank you so much, and I'd like to answer any questions that you might have. Yes. I will, yes.
How do you relatively uniformly infuse?
That's a good question. How do you uniformly get those voids filled, all those little pore spaces? It's not simple. It's not simple. Part of it is the wood that you choose, because not all woods have open porosity. But second is, you can, if they have open porosity, by simple vacuum resin transfer, just by the pressure you get from the atmospheric pressure, you can pull it through. But what we do for scaling up is we apply an overpressure. We force it right in. We evacuate the charcoal and then force the resin in. Evacuate with a vacuum. Yes? It is exactly the way they make railroad ties, which has been scaled up.
there other kinds of polymers that you can use, or is just one?
There's certainly other polymers. I haven't had the time to use other polymers. I've been using ones that are very low viscosity for time and slow curing rates for time issues, but certainly other polymers are possible. That's a good question. What's the typical polymer content of this final product that I sent around? It's going to be on the order of 75% by volume. So it's a lot. So if you look at the costs of making this in terms of the raw ingredient costs, a whole lot of it is in the polymer you're pumping into it. Good question. Have we looked at the thermal properties of these materials for the composites that that I showed, the ones that are going around, the ForestPlate material? We haven't done a thorough look at it, the polymer degradation part of it, but certainly in terms of what this carbon polymer composite, thermal degradation of that composite will begin first with the polymer that we put in it, because it is an organic that will decompose at a few 200 or 300 centigrade, begin decomposing. If you look at the carbon itself, it won't thermally decompose in reasonable circumstances. The carbon itself, as you probably know, can take virtually any temperature you want to throw at it if there's not oxygen around. So the typical number that is thrown out there, when you get to 3,500 degrees centigrade, vapor pressure might start playing a role, and you'll start to decompose the carbon, the solid carbon, but the solid carbon itself is very temperature resistant. The composite's a different story because it's the resin. So we haven't looked at decomposition. We have done a little bit of work in looking at thermal conductivity of the carbonized wood, but not a whole lot. We've not looked at that. Some other researchers have done a little bit of that, but we have not. The carbonized wood or charcoal will be fairly insulating because it is, first of all, say 75% air, and then the remaining solid structure is carbon, which is a glassy carbon, which in the categories of solid carbons is the least conductive thermally because of the carbon structure. I don't have a good database on thermal properties, but I have a sense for what it's like. Yes.
By acid treated wood can get a high charcoal yield. What's the final charcoal pH process? This is the second question.
What was the last part of the question? What was the final
pH? Yeah.
The two-part question, as I understand it, why does the pretreatment give you a high carbon yield? And what is the final pH? I don't have an answer for the last one because we never tested the pH. The first one, why does it result in a higher carbon yield? That was a question that I kept posing to my chemistry student, and we never got a good answer from that. Obviously, it changes the decomposition mechanisms, but I don't have a good understanding myself, and neither did the student, of the altering decomposition mechanisms.
You have your PGA here for the untreated sample, so you don't see a final yield for those the treatment.
If I understand your comments, looking at consistency of carbon yield with the various different bits of information I gave, what was clear to us is that the carbon yield, the solid carbon yield when we treated with sulfuric acid was greater. The thing that throws that off is the TGA that I showed. It showed the same mass at the end. So that TGA did not reflect well the situation we found when we did decomposition in another chamber, in a furnace. When we did thermal decomposition in a furnace with good control over the atmosphere, we found a higher solid carbon yield in the treated wood compared to the untreated wood. It was presumably under nitrogen, and I don't have a good explanation why those mass yields look the same, if that's what you caught. They looked the same, and when I prepared that slide the other day, I was thinking that's going to elicit just this question. And we were looking at that data a year ago, and I was questioning it as well. And I think that their TGA had a small amount of oxygen. It wasn't pure nitrogen. So I think we had some issues with control of the gas volume in the TGA. Yes?
Have you looked at the formation of polymer hydrocarbons in the pyrolysis process, or are there any issues surrounding that?
We have not looked into it. I'd be interested in looking in it. We have spent very little time in looking at that pyrolysis byproduct, that vapor, that oil. That's a new area for me, one that I'm interested in partnering with people on. Let me hear.
Safety, health and safety on the railroad, if you have a powerful furniture, is that a new issue that has to be considered, or how do you look at it?
The question of safety with this ForestPlate material, and with regard to, I think, putting something on it? Fires. Yeah, good question. The combustion safety issues. Yes, that's something that we always look at when coming up with new materials for homes, and that is what kind of vapors come off when it burns. And we didn't look at that yet, but certainly that's something that's on our radar screen if it were to go into home products, countertops or something like that. We'd have to get it fire rated, so that we'd have to look at the compounds that come off and make sure that what the challenge is going to be the type of polymer we infuse into it. What kind of compounds does it give off? So we haven't looked into that yet, but certainly it's one we'd have to. Yes?
What kind of polymers you use for this carbon-polymer composite?
The question is, what kind of polymers did we use for the carbon polymer? We used an epoxy system, and I don't recall the exact type of epoxy, produced by Goujon Brothers.
In this composites, this polymer is 70% by volume. How much it is by weight?
It's roughly the same, because the polymer is about 1 gram per cc, and the charcoal is not a whole lot different than that, depending on how you measure density. So they're roughly the same.
You try different amounts of acid for pre-treatment? And
yes, the question being, did we try different amounts of acid in pre-treatment? We did, and I don't know if it was in some of this data, or I know I did not focus on it, but part of the effort was what concentration of sulfuric acid treatment would optimize the results. And they, for the series of experiments that were done, the pre-treatment solution was 10% sulfuric acid. Yes, there was 7 to 20, I think, and yeah. Yes?
I'm not sure if I'm interpreting the graph correctly, but there was one graph where you showed temperature versus mass decreasing rate.
Yes.
And I noticed a difference between, how the mass decreased. So could you use that difference as a way of using one material or other in in a building construction where you would slow down how fast something burns down.
The question or comment being that the TGA results indicated the different temperatures that treated versus untreated wood began to significantly lose mass. And is that helpful if we tried to better understand the materials being able to withstand a fire? I would think it would be useful, but I guess I first I separate in my own mind the difference between things decomposing with oxygen and things decomposing without oxygen. So, everything we look at is without oxygen. What I've shown is hopefully without oxygen. So once you have oxygen playing a role, then it's a whole different game. You have fire. Yeah.
You saw in your TGA the difference, like with treated wood, you are seeing the rapid decrease in the mass, right?
Yes.
Do you think that it's due to the hemicellulose starts degrading first, then cellulose, and then lignin? Do you think it's doing something like depolymerizing those things first, and then you're seeing those degradations?
The question or comment is that by pretreatment, we showed how lower temperatures began that mass loss. We got mass loss at significantly lower temperatures, and maybe that was owing to the influence of the treatment on the different components in the wood of hemicellulose, cellulose versus lignin. And that's certainly a plausible reason. It may be that it attacks the lignin and cellulose primarily. Maybe there are people here who understand that a whole lot better than I do. I don't know. But that's certainly a possibility that it could be decomposing some of those, or at least facilitating their decomposition. But it's just a guess at this point. It's something I'm very interested in and was hoping we'd make more progress on, because I like to understand the mechanisms. Could you? Could you repeat that for everyone?
I just said that the sulfuric acid can hydrolyze cellulose to simple sugars, but lignin is less impacted.
Okay, so it's for what you understand.
When you use the acid treatment, you basically partially hydrolyze
The cellulose.
cellulose portion of the wood.
Yes.
That's why you see that when you do the TGA experiment, you see a rapid weight loss for the acid treatment.
Over to the lower temperatures, right. So if I had you in the game